Okay, this is the pre-class lecture for Monday, October 29th. So we've talked about substitution, where we take our nucleophile and we react it with a carbon with a halogen leaving group. And so far, that's all. The only types of leaving groups we've had have been halogens. And either that nucleophile comes in and displaces the leaving group to form then our final product, and the leaving group becomes an anion. Or we can, and this would be our SN2 mechanism, or we can have the carbon halogen bond break, form then a carbocation, and then have the nucleophile come in and add to the carbocation to then give us the final substitution product. And this, of course, would be an SN1 mechanism. Now, closely related to SN1 is the idea of what we call unimolecular elimination. And so what can happen is this. Let me start with a very specific molecule. Let's start with tertiary butyl chloride. Now, what can happen with tertiary butyl chloride is, since it's a tertiary halide, we can break the carbon-chlorine bond and form our tertiary carbocation, which is a stable carbocation. Okay. But then it becomes an issue of timing as to what will happen next. Whenever you do an SN1 reaction, there's always the possibility of doing a side reaction called elimination. And so the carbon that was attached to the halogen is called the alpha carbon. And any carbons then attached to the alpha carbon are called the beta carbons. And on down the line, then you would have gamma and delta. Any hydrogens attached to beta carbons are called beta hydrogens. So over here, it's the carbocation that's the alpha carbon. Let's say I had a beta carbon here, and then I have my beta hydrogen there. So what can happen, particularly if you apply heat to this reaction, is that before the nucleophile comes in and attacks the carbocation, you could end up eliminating the H+, eliminating an H+, from a beta hydrogen. And so what could happen is we could break this carbon-hydrogen bond, move the pair of electrons to that carbon. So therefore we would lose H+ from this molecule, and we would form a double bond then between that alpha carbon and one of the beta carbons. So we can form an alkene molecule. And so it turns out that for this reaction, this is elimination, because the net result is that if I put my Cl- down here, the net result is that I've lost HCl from this molecule. So if I just rewrite this molecule here, the tertiary butyl chloride, the net result is that I've lost or eliminated HCl from this molecule to form my alkene, my carbon molecule with the double bond. Okay, so this is an elimination reaction. And the key thing about elimination reactions is that you will form the double bond between the alpha and beta carbons, and you will lose a beta hydrogen then to form that carbon-carbon double bond. Now, this is elimination, so this mechanism is an E mechanism, to contrast with SN mechanisms of substitution. There's two types of eliminations. One is unimolecular and one is bimolecular. We're going to deal with the unimolecular reaction today. So just writing out the steps of this mechanism as two discrete steps. We've got, starting with the tertiary butyl chloride, we break the carbon-chlorine bond to form a Cl- and this carbocation. That's step one of the mechanism. And then in step two of the mechanism, we end up losing the beta hydrogen I'm going to write it this way. We end up losing the beta hydrogen and bringing that pair of electrons to form the carbon-carbon double bond. Okay, so here's my two steps of the reaction. Well, for unimolecular elimination, it turns out that the rate of this reaction is equal to K times the concentration of the alkyl halide raised to the first power. Okay, and actually, if you look at this molecule, there's only one molecule involved, and that's a tertiary butyl chloride. So this again becomes a unimolecular reaction. It's first order overall, and it turns out that this step right here, oops, that's not the fast step. The first step is the slow rate determining step. And then the second step turns out to be the fast step. So where have we seen this before? We've seen this before with SN1. So it turns out that whenever you do an SN1 reaction, because you form this carbocation intermediate, you will get usually a mixture of SN1 and E1 products. And so you'll get a mixture of unimolecular substitution and unimolecular elimination in this reaction. Okay, so we're going to modify our chart later this week on Wednesday with basically by adding SN1 and E1 together whenever we predict an SN1 reaction. We're always going to get a little bit of E1 product as well because they share the same first step. It's really a question of timing as to whether or not the nucleophile attacks this carbocation or we eliminate one of the beta hydrogens. So for unimolecular elimination then, we have to be able to write the products. And so we have to be able to identify the alpha carbon, all of the possible beta hydrogens that I can lose, and then write the alkene products. So let's say that I gave you this alkyl chloride. And I said, let's do E1 elimination on this. Now, first step in the mechanism then is going to be to break the carbon-chlorine bond and to form then our carbocation. And so just for the sake of argument, let's write the transition state, which is delta minus and delta plus for the carbon and the chlorine, as that moves on then to form the full-blown carbocation. Okay. Now, if we're going to do elimination, we need to find all of the possible beta hydrogens that I could lose in the second step to form the double bond. So here's my alpha carbon. There's my beta carbon, there's my second beta carbon, and there's a third beta carbon. And so what I'm going to do is I'm going to write then each of those beta carbons has a beta hydrogen attached to it. It's just going to be a CH, and then there's a CH3. I'm going to erase that too. Okay, so there are my three beta hydrogens attached to then the alpha and the beta carbons. So how many different products can be formed by the loss of these three beta hydrogens? Do I form just one product, two products, or three different products? So let's call this beta hydrogen A, let's call this beta hydrogen B, and let's call this beta hydrogen C. So let's just say for the sake of argument that I lose HA. So if I come down here and I lose HA plus, I'm going to form the double bond between the first carbon so let's call that product A. So if I lose HA, pair of electrons moves here, that's going to give me that product. Okay, how about I lose HB? So I have HB move its pair of electrons here to form the carbon-carbon double bond. What product am I going to get? Well, I'm going to have my CH3 over here attached to the carbon that's doubly bonded to the CH2. And then over on this side, I'm going to end up with my CH2, CH3. So here's product B. Now, let me ask you, are product A and B the same product, or are they different? And if you said they're the same, you're right. What's attached to this? Let's look at the carbon-carbon double bond. What's attached to the carbon-carbon double bond? Over here, I've got two hydrogens, a methyl and an ethyl. What do I have over here? Two hydrogens, a methyl, and an ethyl. So it turns out that product A and B are the same products. Okay, and when we learn about naming alkenes after our second exam, then we could go ahead and name them and we could figure out whether they're truly the same. But what we need to do in this case is see what is attached to the double bond. In this case, it's two hydrogens attached to one carbon and a methyl and ethyl attached to the other carbon. This has two hydrogens and then one methyl, one ethyl attached to the other carbon. So therefore, they are the same molecule. But now how about we lose HC? So what if I lost HC and had that pair of electrons move to form the double bond there? What would I get? Well, I would get my CH3, which is this group right here. I would have my CH3 on top, and then I would have my double bond to the CH, which is then attached to the CH3. So I form my alpha beta double bond there in this molecule. Now, is this molecule different? Well, I have two methyl groups attached to the left carbon and a hydrogen methyl attached to the right carbon of the double bond. And so therefore, product C is a different product. Okay, so we have three possible products. Two of them are the same and then the third one is different. So I really have two different products in this reaction, two different alkene products. Okay. Now, I'm going to rewrite these two products being formed on the next page. And then what I'm going to do is, let's write the transition state that you would get for the formation of each one of these products, because we haven't written the transition state for the second step yet. And then we'll deal with another question that I would have. So let's take this, what we said was carbon or hydrogen A here, beta hydrogen A. And now let's bring this pair of electrons up here, and now let's write the transition state. So what would the transition state for this reaction be? Well, let's write this core of the skeleton first. Which bond is being broken? The CH bond is being broken. Now, if I come down here and write my final product, what bond is formed? If you said the double bond, this double bond is being formed, you're correct. And so the transition state, first of all, dealing with which bonds are broken and formed, would look like this. I'm breaking the CH bond and I'm forming a CC double bond. Okay. So then I have to look at charges. And down here I'm going to have my H plus. So what is this hydrogen is on its way from a 0 formal charge to a +1 formal charge, therefore that hydrogen has a slightly positive charge. How about the carbon? The carbon goes from +1 to 0 formal charge, therefore the carbon here has a delta plus charge. Notice the other carbon doesn't have a charge in either the reactants or the products, and so therefore there's no partial charge on it. Okay, so now in this case, this is the mechanism to form product A. Can we write the mechanism to form product B then? Or sorry, product C. Okay, can you write the transition state and then the final product for C? If you can, stop the video, go ahead and write it, and then we'll see if you're correct. So I'm going to take this pair of electrons, move here to form the double bond. And let's just go ahead and write the final product, and then we'll take the sort of average and that'll give us our final, our transition state. Okay, so in the transition state, what bonds were being broken and which bonds were being made? The carbon-hydrogen bond is being broken. The carbon-carbon double bond is being made. The carbon's on its way from +1 to a 0 formal charge. Therefore, it gets a delta plus charge. This hydrogen is on its way from being 0 formal charge to a +1. Therefore, in the transition state, it gets a delta plus charge. So there's the transition states for the formation of product A and product C. Those are the two unique products of this E1 elimination reaction. Now, those of you that are psychic are probably saying, well, I know the next question he's going to ask. And the next question I'm going to ask is, I just did a reaction that formed two products. Say it with me. What's the major product of the reaction? And more importantly, why is that the major product of the reaction? Well, that leads us to the next part of elimination, which is predicting the major products of the reaction. It turns out that for E1 elimination, the major product is the most stable product. And you might say, oh, well, great. So of these two alkenes, A and C, which one's the most stable? Problem is we don't have rules for stabilities of alkenes. What do we have rules for? Well, stability of radicals, the stability of carbocations, stability of like Newman projections, chair cyclohexanes, but alkenes isn't on our list. So we have to talk about what makes an alkene the most stable. Well, an alkene, a carbon-carbon double bond, can have up to 4 things attached to it. And it turns out that an alkene is an electron withdrawing group. Which basically means that the double bond becomes more stable when delta minus charge is pushed into it. And what do I mean by that? Well, how many times this semester have we taken and written the structure of an alkyl group and then said, well, normally the carbon-hydrogen bond is considered to be relatively nonpolar, but we do have times when we say the hydrogens are delta plus, and they became that way at the expense of the carbon, which is delta minus. What does this carbon minus, what does this C minus do then? It pushes electron density. How many times have we seen that happen this semester? Well, by my memory, 2. One when we explained the stability of radicals, and the other one, just last week, when we looked at the stability of carbocations. Well, here's the third case of where we're going to use this pushing of electron density. It turns out that if you have an alkyl group attached to a double bond, it can push electron density then into the CC double bond and make the alkene more stable. Therefore, the more substituted the alkene, and I'm going to write with alkyl groups, the more stable it is. Okay. So the best case scenario is it's got 4 alkyl groups attached to it. That would make it the most stable. Worst case scenario is it has no alkyl groups attached to it, at which point it's C2H4. Well, that's ethylene, that's a gas, and we don't really use it that much. But in between, you could have 1 alkyl group, 2 alkyl groups, 3 alkyl groups, and then the most stable at 4 alkyl groups. So, the more substituted the alkene, the more stable it is. So it turns out that there was a Russian chemist named Zaitsev, and your book uses this spelling of Zaitzev, Zaitzev, Zev. I sometimes will use the this spelling of it. The problem is Zaitsev was a Russian chemist that published in a German journal, and so his name just got messed up in the translation. But Zaitsev actually studied elimination reactions, and what he found was that when you did a reaction, when you did an elimination reaction, you got the most substituted product as the major product. And this became known as the Zaitsev product, or Zaitsev elimination. Later, we took his correlation that you got the most substituted product as the major product, and we then determined that the most substituted product was indeed the more stable product, and then proposed the explanation of that by the carbon pushing electron density in. So Zaitsev made an empirical observation. He gets a rule named after him, but he really didn't explain why you got the product that you did. Okay? So when we do E1 elimination, we're going to get the Zaitsev product, which means we're going to get the most stable, which is the most substituted product that's an alkene. So now let's go back to products A and C. Can you figure out which of these two products, either A or C, is the more stable product of the reaction, and therefore would be the major product of this elimination reaction? Well, if you said, well, wait, what if I don't know? How am I going to judge that? Well, then let's go back to basics. I'm going to use my eraser here because I'm going to take this carbon that was in the double bond, and I'm going to add, that was a CH2, so there's two hydrogens here. So how many alkyl groups are attached to carbon A, or to product A? Well, I got a hydrogen, a methyl, and an ethyl. So therefore I have two alkyl groups attached to the double bond. How many alkyl groups are attached over here? If you said 3, you're correct. The methyl, the methyl, the methyl, and then there's a hydrogen that isn't an alkyl group. So what's the major product of the reaction? Product C. Why? Because it has the most alkyl groups attached to the double bond, therefore it is the most stable. Okay, so E1 elimination always follows what we call Zaitsev's rule, which is that you form the more substituted double bond. But in order to be able to predict the product, you got to be able to write it, which means you have to be able to lose the beta hydrogens and then form the double bond between the alpha and the beta carbons. And then you can go ahead and count up how many alkyl groups are attached to each of the double bonds. Okay. Now, just to go back for a moment, I started with doing the elimination of tertiary butyl chloride. Why did I start with that one? Because it turns out that there's 3 beta hydrogens, and so there's 3 sets of beta carbons, but it doesn't matter what my elimination product is, whether it's the CH2 bonded on this side, or whether it's the double bond to the CH2 on top, or whether it's the CH2 that's double bonded to the right. In this case, I get the same product in all three cases. This carbon has two hydrogens. This carbon has a methyl and another methyl. This carbon has two methyls, two hydrogens. Two hydrogens, two methyls. Same product. So it was only when I went to the tertiary pentyl chloride did I see the possibility of forming two products. Now let's amp things up here a bit. And say I want to do E1 elimination on 1-chloro-2-methyl cyclohexane. Can you write the two possible products of this reaction and then tell me what the major product of the reaction is? If you think you can do that, then go ahead and stop the video and try it. If you don't, then let's start with a mechanism. And let's break the CCl bond. And give me that carbocation. That's my here's my alpha carbon. Here's my beta carbon. Here's my other beta carbon. I don't like that that's small, so I'm going to come back over. So I'm going to come over here, and I'm going to write it a little bit bigger. So here's my carbocation. Here's my alpha carbon. Here's my beta carbon, and here's my other beta carbon. Now, how many are there hydrogens attached to this beta carbon? Yes, there's two beta hydrogens. Is there a hydrogen attached to this beta carbon? Yes. There's my beta carbon, or there's my beta hydrogen. So let's call this one A, and let's call this one B. So if I take my pair of electrons and move it here and lose the HA plus, what's my product going to be? Well, it's going to have the double bond there, right? And then down here I would just have my normal CH3. If I was going to write the transition state for that step, just to have practice, I would write a partial bond between the carbon and hydrogen, and then my double bond forming, with my delta plus on the carbon and delta plus on the hydrogen. And then down here my CH3. So there's my transition state for forming, let's say, product A. If I took the pair of electrons, I'm going to add another color here. If I took this pair of electrons from HB and I moved it there instead, I'm going to lose HB plus, and that's going to give me then the double bond down here, and product B. My transition state for that step would look like this. So I had a partial double bond, partial breaking the CH bond, and then a delta plus on what was the carbocation and a delta plus on the hydrogen that's leaving. So there's my transition state to form product B. So which one's the major product, A or B? When we first start looking at cyclohexane rings, they kind of freak people out because people are like, well, I can't count how many groups, alkyl groups, or how many how many hydrogens are attached to the double bond. So let's do this one by hands. Now, there's two alkyl groups to this attached to the carbon-carbon double bond in product A. So there's two alkyl groups. And if you're saying, I don't see where that comes from, hold on for a second, I'll tell you. And over here there's three alkyl groups attached to the carbon-carbon double bond, which means that this product B, is the major product of the reaction because it's the more substituted double bond. Now, how did I know there's two alkyl groups over here? Well, here's my CC bond, and my CC bond has four things attached to it. It's got a CH2 group here, a CH group there, a hydrogen there, and a hydrogen there. If you don't like these alkyl groups, you can only have four things attached to a double bond. If two of them are hydrogens, that means the other two are alkyl groups. So this has these two alkyl groups, the CH2 of the ring and the CH of the ring. Does it matter if they're in a ring? No. It just matters that they're a carbon. Actually, it matters that they're not a hydrogen. So this A has two alkyl groups. So then if I put my hydrogen into B, what do I have? One alkyl group, two alkyl groups, three alkyl groups, and one hydrogen. So there's my three alkyl groups. And the molecule B that has three alkyl groups attached to the carbon-carbon double bond, that is more stable by Zaitsev's rule. Okay, so product B would be the major product of the reaction. Okay, so for us to be able to do E1 elimination, we need to find all of the beta carbons, all of the beta hydrogens, be able to do our elimination mechanism, and then look at the product and see which product has the most substitution. That's going to give us the more stable alkene. And I'll just say that it doesn't matter what the alkyl group is. It doesn't matter if there's one methyl, one ethyl, 100 carbon chain. If a double bond only has one alkyl group attached to it, that's all it has, regardless of the identity of that molecule. Okay, so this is how we do elimination that's unimolecular. Okay, and so what we'll do in class on Monday is we'll look at some problems. I'm going to take Friday's class and Monday's class and kind of put some things together and come up with some magical rearrangements for some of these molecules and say, how did I get that elimination product? And I'll get it through a 1,2 hydride or a 1,2 methyl shift. Okay, but this is the third mechanism of the reaction, or of the reactions, E1 elimination. And the key is that E1 is always closely tied to SN1 because they share the same first step. So when you get SN1, you always get a little bit of E1 product that goes with it. Okay.